Bismillahirrahmanirrahim. Today's topic is discretization, and this is the first thing that catches our attention, and it is usually the last thing also. The rest of the steps from 2 to 7, it is more or less mechanical. So whatever we do here has direct bearing on the results, and if the results are not good, then we have to come back to discretization. What we are going to do today is going to be bare minimum. It is a vast field and a lot of experience and know-how is required to master this. By discretization, we mean that the physical domain is subdivided into a finite number of discrete elements. Now, at least three things concern us here. Number one, what kind of elements? What type of element to use? And this is linked with another problem. Can any simplification be made? In our model? Now, when we talk about simplifications, we must be faithful to the problem. We cannot change the problem into another problem. So as long as we don't change the nature of the problem, any simplification is welcome. If we have to change the nature of the problem, then what we'll be doing is answering a different question, not the question that we are concerned with. Now, once this is decided, the next question will be how many elements? And the third one, how to number the elements and the nodes. Now, this could have bearing on the efficiency of our scheme. So let's take up these questions one by one. Let's start with any simplification that can be made, and that brings us to the topic of dimensionality or geometric approximation. Now, all structures in the world and all their components, they are 3D, obviously. And if you take any node in any one of them, if you discretize them and you take any node, then there are 3 degrees of freedom for each node. Go in the x direction, y direction, z direction. We're talking about displacements here. However, 3D analysis is expensive. Computational resources are always at a premium. Now, it is often possible to reduce the computational cost of a full 3D analysis by using a reduced order model. For example, in reality, it is a 3D body subjected to some forces, but it can be reduced to a 1D problem or a 2D problem if the geometry and loads satisfy certain conditions. So if that can be done, then it is always welcome, because it will cause a drastic decrease in the computational cost. Now, This is not new for you. You have already done a problem in which we converted a problem to a 1D problem. If this is the problem that we want to do, like we did last time, then it is subjected to some force here. And although it is obviously a 3D body, but the force is such, and our quantities of interest, that is the displacements, the strains, the stresses, they are all aligned in the x-axis, x direction only. So we were able to convert this problem into a 1D problem. We wanted to find u, which was a function of x only. This is what we mean by reducing the order of a model. And this is actually, this we call a bar element, linear bar element, but it is also called, incidentally, a truss element, because all truss members are two force members. There's only axial deformation causing axial stresses. A truss could be 2D or 3D, but each member of the truss, that is 1D. And we are going to see truss problems very soon and in detail. But this is not the only simpler domain that we will be dealing with. Other simpler domains of lesser dimension. Let's call this for what it is. The dimensionality has been reduced. Beams, plates, shells, and we'll consider some of these in future classes. Torsion bars. Torsion bars could be cylindrical or non-cylindrical, of for example square cross section or any other cross section. So these are two different things. Apart from these, there are classes of problems that are called 2D problems. They are also simplifications of 3D problems. There are two classes of problems called 2D problems. One is called plane stress problems, the other plane strain. I won't be going into too much detail here. You're familiar with these from your solid mechanics course. I'll just stress one or two important points which have a bearing on our FEM analysis, especially discretization. This is a thin object. The loading details and the geometrical details, they are all in one plane. Both its faces are free surfaces, so there's no stress here. In the thickness direction, we call it the z direction, and the plane of the problem is xy. So if there's no stress in the z direction on the two faces and the plate is thin, then it is reasonable to assume that stress in the z direction throughout the thickness is 0 or very close to 0. So there's no stress in the z direction, or as we call the out of plane direction. If that is the case, then we can call it a plane stress problem, and we can mesh it in this plane. Just a rough mesh. We only need to mesh it in this plane. And so on. Now, what this means is, if it was a 3D problem, then we would have needed to, for example, this is the problem. There would have been some thickness here, and we would have needed to mesh the thickness direction also, and then we would have needed not area elements but volume elements, or what is called solid elements. This is a 3D mesh if we would have taken that route. Now these are all area elements. You can also call them 2D element. This is called 3D element. Now, furthermore, you would have needed some 3 or 4 elements in this direction, at least, because there's something called aspect ratio, and you'll become familiar with this as you do some analysis. Aspect ratio means for a 3D, 3 dimensions, 1, 2, and 3. These, for any element, they cannot be drastically different from each other. There are problems of conditioning, and accuracy is adversely affected if the aspect ratio is too high. So we need to keep the aspect ratio in check. So if we want to mesh this region closely, that is, we need to use a fine mesh because there's a lot of stress gradient there because of the pore. Then we are required to mesh this direction also using a fine mesh. So that means that, first of all, one source of simplification of the model results from the use of area element as opposed to solid element. It's a huge difference, first of all, because the computational cost of a solid element is many times more than an area element. Furthermore, we would have needed to use more solid elements, at least 3 or 4 times more than what we are using here. Whatever the number of elements in this plane, you would have to multiply it about 3 or 4 to get the total number of elements. So it's a huge saving in cost of the analysis. Now, as compared to this plane stress problem, this is a plane stress problem. The other class is the plane strain problem. Let's look at that. This is a dam which is constrained on both sides, and the loading, that is the water, that is on one side, but it is constantly there. The support from the ground, it is again throughout the length, it is constant, and its weight, it is also evenly distributed throughout. So all the loading is consistent throughout. There is no change throughout the dam. Constraint on both sides means the strain in this direction. By convention, we call it this, again, the z direction. This is the z direction. The strain in z direction is 0, and these are the x and y dimensions, the in-plane dimension. There is no load in the direction of z. This means that any section is as good as any other section. We can take just this section, mesh it. Obviously, we'll need to apply the pressure of the water on this side. There'll be reaction from the ground. There'll be weight of this downwards. But any section is as good as any other section. We could have taken this section instead. It could have been the same. So again, we can just mesh this plane again with area elements. And in this case, the saving of computational resources is even greater than the last problem that we took up, because consider you mesh this area elements, let's call it the number n, number of elements n. Now, if we were to mesh this as a solid body, then we would have needed elements in this direction as well, in this direction, and using the same considerations that we talked about, we would have then needed elements like this, something like this, solid. And because of the considerations of aspect ratio, we couldn't make it, for example, something like this, very long. This causes a lot of problems, and accuracy suffers. So you would have needed to divide this into many number of elements, and if this dam is many meters long, then you can imagine how many elements you would have needed. So none of that is needed now by the careful identification of a reduction possibility for dimensionality of the problem. Now this simplification was regarding dimensionality or geometric approximation. Now there's another avenue of simplification. And that is simplification through symmetry. Now there are at least 3 types of symmetries, and let's take them up one by one. Let's take this vessel or pipe which is subjected to an internal pressure. The internal pressure will be on all the walls. I'm just showing. If you consider this from the top, then what I mean here is pressure P is applied everywhere. Now there could be some other pressure on this top surface also, but again this needs to be pressure on the top surface. Again, this also needs to be consistently applied throughout, constantly applied throughout. Now if that is the case, any plane of this problem is as good as any other plane. We could just take this plane, instead of modeling this body with 3D elements, which will be a handful, we could have taken this plane also. Obviously it would have been the same, and any other plane, for example this one or this one, it's essentially the same. So we can just model it like this, provided we apply the pressure on this plane. Again, this pressure needs to be constantly applied to all planes, otherwise this kind of simplification is not possible. Similarly, this pressure needs to be, and there could be some external pressure as well. If we are able to make this kind of a simplification, what results is this. What we do is we just model this problem like this in 2D using area elements, and we don't need to use 3D elements, which again obviously results in considerable saving in computational cost. Now this kind of symmetry, because this is a plane which, if we revolve around this axis, if we revolve 360 around this axis, we get this solid body. So this sort of symmetry is called aptly axial symmetry. It's also called axisymmetry, same thing. Now this is so common that all finite element packages, they have a special element for these problems. Now all these sections, and this is a good representation, this one, Now, if you take this plane is constrained to move in the circumferential direction theta. So all points will move. Now these points could the deformed shape of the body could be something like, after the application of the pressure, it could be something like this. So the radial direction motion is possible. Motion in the longitudinal direction, we call it z. This is r. This is also possible, but there is no motion in the circumferential direction. This section, this will, after the application of the internal pressure, this will remain in its own plane, and no point on it can move in the circumferential direction. Hence, we can just model it like this. Now consider another problem. Let's say this is a thin plate which has been reduced to a 2D analysis, considering it a plane stress problem. Now you just need to mesh this plane with area elements. So this is one stage of simplification already achieved. But can this be further simplified? If we draw these two lines at the middle, this one and another line, another center line, this one, whatever is happening on the left hand side should also happen on the right hand side, because the geometry as well as the loading are mirror images of each other. Talking about this line. And now consider this one, this horizontal line. Again, you can say the same thing. Upper half is a mirror image of the lower half, both in terms of geometry as well as loading. So we don't need to mesh the whole body now. Only 1/4 will suffice. Let's do this like this. If we model this body like this, we apply the loading on this part, its fair share, and what we need to do now here is we must constrain this problem. Now here, this line, the displacement here is 0, because this nodes on this line neither go to the left nor to the right, because again there is symmetry on both sides. So there is u displacements, x displacements, they are 0 on this line. When it comes to this line, no point on this line can either go up or go downwards. So here the v displacement is 0. As long as we do this, then we don't need to mesh the whole thing. All we need to do is something like this. Mesh this 1/4, and whatever number of elements you use, and so on. We will mesh this area also, but whatever the number of elements used ultimately, let's call it n. If you hadn't spotted this chance for utilizing symmetry, you would have needed 4 times n number of elements. So again, first you reduce this problem from a 3D problem to a 2D problem, let's say plane stress problem, and then furthermore you reduced it further to 1/4. So this kind of symmetry, where a plane is there, like there are two planes here, this plane and this plane, these two planes, and it is symmetric about these two planes. This type of symmetry is called planar symmetry. So this is the second of the 3 types we're going to discuss. Planar symmetry. Again, very extensively used, and you should always try to spot if there is a planar symmetry anywhere in your model, because it will help you a lot in terms of reducing the computational cost. Now consider this problem. Let's say there's some pressure, internal pressure throughout this inner surface, and there could be again some pressure or some pressure on this face also. Uniform pressure here, and again uniform pressure. Now, this is not an axial symmetry problem or an axisymmetric problem, because there is no plane that you can just sweep around 360 degrees and you get the problem in 3D. These holes don't allow that. So in this case, we can take this part, the part in gray, out. So something like this. There's a hole here. Now, this is the circumferential direction. Then, this is the circumferential direction. Then we need to constrain this. All the points on this. In our case, there'll be nodes, not points, but all the nodes on this, if they are constrained not to move in the circumferential direction, there's no problem in moving the radial direction, because as a result of this internal pressure, the new position may be something like this. But the point is, this plane, all these points will remain on the same plane. It could move radially. This is the radial direction. It could move radially, but there is no movement in the circumferential direction. This is the circumferential direction. We can show similar deformation, exaggerated in this case also. The plate will extend in length, it will contract in width, but the point being, on this plane, the points on this plane will move in the y direction, but they won't move in the x direction. Similarly, on this plane, points, they will move in the u direction, no problem, but there'll be no motion in the v direction. So here v is equal to, and that is what we had already said here. So similar considerations work here. Now this is as far as symmetries are concerned, and this symmetry, this final one, this symmetry is called cyclic symmetry. So we have axial symmetry, planar symmetry, and cyclic symmetry. So we have addressed the first problem, what type of element to use. Now we take up our second question, that is how many elements to use. As we increase the number of elements, the element size decreases and the accuracy increases. But the question is how far to go. And this is where we need to do something called convergence. Convergence check. Without this check, we don't know whether our solution is accurate or not. And this is how we do it. We essentially plot a graph. On the x-axis, we have the number of elements. On the y-axis, we have some quantity of interest, for example, stress or displacement. Let's take this as stress. Now let's call it maximum stress. For a problem, you have a point where the stress is the highest. You do an analysis for a certain number of elements and you read the value of stress, then of maximum stress. Then you refine the model, that is, use more elements and the stress value will rise, and you refine it further and the stress value will rise. But as you move along, the difference between successive simulations, it will tend to decrease. First there will be a big gradient, then the slope will decrease, and at a certain point you will realize that though the value of stress still increases, but now we are talking about very small increases. After this, as you keep on increasing the number of elements, you'll get a more accurate solution, yes, but at what cost? It won't be worth the trouble. Now you have achieved a reasonable degree of accuracy, and this is the time to stop. Beyond this, for a very small increase of accuracy, you'll need a lot of computational resources, and that is not advisable. So this is what is called convergence check. Mind you, this is the only way you can check whether your analysis has any validity or not, because generally speaking, we don't know the answers. We have nothing to compare this to. So all we can do is compare our results with each other. And the moment you feel that now the comparison shows you that some sort of convergence is achieved, that is the time to stop. Now, one point that I want to stress here is that because the computational resources are always at a premium, you must use your number of elements wisely. That is, you must use something called biased meshing. And we discussed this in the introduction as well. By biased, I mean, let's take the problem of the flat plate subjected to loading. We just saw this problem. Now, we know that a lot of stress concentrations will be in this area. So we must make the mesh very fine mesh here. But it would be a mistake to make the whole structure using the same fine mesh, because it will need a lot of elements. In this region, for example, in fact, the bulk of this problem, you don't need a fine mesh at all. So you should make the mesh rougher here. This is rough mesh. At least it should be. Now the problem is, from going from fine to rough, sometimes there's a drastic change in the size of the element and or a drastic change in the shape of the element. Now whenever this sort of distortion takes place, there are many indications, there are many quantitative measures of gauging these distortions, or which will result in ill conditioning. Aspect ratio we just discussed when we were talking about plane stress and plane strain simplification. There's something called skew, this taper, and there are internal angles. Now there are, for all these measures, there are some acceptable limits, but more on that when we discuss these aspects in detail later on. So we have addressed this question also. Now we take up the last of the questions. How to number the elements and the nodes. How to number elements and nodes. Now, first of all, does it make a difference? Well, let's see. Recall this problem. We'll not be focusing on numbers anymore, just the constitution of the K matrix. Recall that this was in our problem, the node was 1, 2, 3, and 4. The element numbers were 1, 2, and 3. Now, the K matrix was something like 1, 2, 3, 4, 1, 2, 3, 4. There's a number here, there's a number here. Then you have this number here. And then you had zeros. Please confirm this. What the numbers were is not important at this point. Now, where do we find zeros and where we find non-zero numbers? We discussed this. Zeros are where the nodes are not connected by one element. For example, let's call this location. This is called 1 3 location, and this symmetrically this is 3 1 location. It's the same thing. If there's a 0 here, there's a 0 here. 1 3 location means 1 and 3, node number 1 and node number 3 are not connected by an element, and they are not. Node 1 and 2, they are connected by element 1. So 1 and 2 means 1 2. So here you have a number. 1 and 1, obviously the diagonal will always be populated because 1 is connected with 1, obviously. Similarly, you have this 1 4 position, again 1 and 4 are not connected. You have this 2 and 4 are not connected. And wherever there is a connection, direct connection, you have a number. Now we come to another property of the K matrix, and that is K matrix is a banded matrix. And by banded matrix, we mean that somewhere along the line, in this case, this is the partition, but sooner or later you'll have a series of zeros. Now, when it comes to memory, we can draw a line here and in this problem, and then we can draw a line here. And recall that it was a symmetric as well, symmetric matrix as well. So what this means is we don't need the system to memorize this part and this part. We only, so in this case, the original matrix was 4 by 4. The only content that we need to memorize is 4 into 2. Why? Because this 2 in this problem, this 2, this is called the bandwidth. So the smaller the bandwidth, the better. Which means we need to make sure to align the non-zero numbers as close to the principal diagonal as possible, so that after that the zeros start and that we don't need to memorize those. Now consider this. Just an experiment. If we had numbered this like this, and there's nothing wrong with this, 1 3 2 4, you'll get the same answers. But now consider 1 and 3 are connected. Now in this case, if this is the numbering scheme, then a number will come here, and 2 and 1 are not connected. 0 will come here. So this means that your non-zero numbers are not concentrated close to the diagonal, but they are spread apart. And that means that your bandwidth for this system, because now you have to include this one also. You cannot put a line like this here. Now you have to include this, the bandwidth will become 3. Moral of the story, you have to make sure that all your elements, they are associated with nodes which have numbers which are as close to each other as possible. So in this case, that condition will be satisfied by 1 2 3 4. That makes sense. It could be 4 3 2 1 also from the left side. 4 3 2 1 is the same thing. The bandwidth will be 2 in both cases. But when you don't follow the scheme, then you get a larger bandwidth. So it means the computer has to deal with more information. Now we have a formula for the calculation of bandwidth, and that is d plus 1 into f, where d is the maximum difference between node numbers in one element. Now, and f is the dimensionality of the problem. This is a 1D problem, which means 1 degree of freedom associated with one node. If there's a 2D problem, it will become 2, and we'll see those later on. So let's check these two. The first one, the difference between in all elements, the difference between node numbers 1, 2 minus 1, 3 minus 2, 4 minus 3, 1. So 1 plus 1, one-dimensional problem. So you get, as expected, 2. We knew this one is 2 in blue. But when it comes to this scheme in green, bandwidth becomes, now let's see the difference between the node numbers, first element 2, second element 1, the third element also 2. So you have to take the biggest maximum difference. So 2 plus 1 into 1 remains the same, and you get 3 as expected. Now this bandwidth is the case when you have the numbering in green. Now 1D problems are easy in the sense that even if you didn't know this little detail about node numberings and the bandwidth, you still have numbered the nodes like this 1 2 3 4. It makes no sense to number something like 1 3 2 4. Nobody would do that, right? So it was intuitive as well, so there was no difficulty there. But when it comes to 2D problems, for example this problem, now let's say there's a beam which is, let's say it's a plane stress problem. You can do it with area elements. Now the problem here is that this is not as intuitive as 1D problem. For example, you could number these nodes as 1 2 3 4 5 6 7 8, come back here 9 10 11 12 13 14 15 16 17 and so on. Or you could number the nodes 1 2 3 4 5 6 7 8 9 10 11 12 13 and so on. Now you could do it either way. This is not so intuitive. Which one is correct? You could do it either way. You could also do it in a haphazard manner. You jump from one node to the third node and then the fifth node, but that makes no sense. But these two make a lot of sense, either one of them. So which one is correct? Now you have a hint in the formula above. The bandwidth and physically also, the bandwidth is dependent on the maximum difference between the node numbers in any one element. So that difference has to be as small as possible for you to get a smaller bandwidth. So in this case, obviously, this is the correct one, because let's call this element 1. This is element 1. Now for element 1, in this case, in the first case, the element 1 is associated with 1 2 9 and 10. Now the difference between the maximum difference 10 minus 1 9. In the lower case, the difference between the maximum and the minimum node number is 5. So it should give you a smaller bandwidth. Let's check this. Bandwidth in this case, and the same goes for all the other elements. If you talk about the other elements, you have the same difference in either scheme. Now you have D plus 1 into F. In this case, D is 9 plus 1 into 2D problem 2, so you have bandwidth of 20. In this problem, the second one, bandwidth is 5 plus 1. The difference is 5 into 2, then you have 12. So what we're talking about here is the lot of reduction already achieved like this. So the moral of the story being, for a smaller bandwidth, elements must be numbered in the shorter dimension. You go like, exhaust the shorter dimension first, then you go to the in the longitudinal direction. This is the way to go, not like this. If you go like this and then come back and then go like this will give you a larger bandwidth. Now one thing needs to be emphasized here, and that is, what if this element was not element numbered 1 but element, let's say 8 or 10 for that matter, doesn't matter. Would the bandwidth have changed? Instead of element having 1 2 9 and 10 nodes, it was element number 8. It doesn't matter. Element numbering doesn't feature anywhere in the calculation of bandwidth. So element numbers don't matter, and that is the same for 1D problems as well. In this problem, for example, this element 1 has nodes 1 and 2, but what if there was element 3 here? It doesn't matter. Still the bandwidth would have been the same. So element numbering doesn't matter in this scheme. So what we need to do is, for 1D, just go in a sequence. From left to right doesn't matter, but don't skip and jump. Just number in a sequence. For 2D problems, number them in the shorter dimension first. What about 3D problem? For 3D problem, there will be a third dimension in there. Now, and there will be meshing in that direction also, because 3D elements are volume elements and solid elements, and there will be mesh will be something like this. Obviously there will be mesh like this also. Now you have 3 dimensions. So a little consideration will tell you that you should again exhaust the smaller dimension first, but in this case the smaller dimensions are 2. For the smallest bandwidth you should first number these and then go to the other column, the third one, fourth one. Now you have exhausted this, the first plane, the smaller dimensions, both smaller dimensions on the first plane, and then you move along the length. This will give you the smallest bandwidth possible for this system. By the way, if you are wondering about this f in the formula, you must realize that for 1D problems, degrees of freedom of the problem is equal to number of nodes. But for 2D problems, the degree of freedom of the whole problem is 2 into number of nodes, because each node has 2 degrees of freedom, x and y direction, u and v. So you have the total degrees of freedom of the system will be twice the number of nodes, and hence for 2D problems you use 2 here. For 3D problem you will have the degree of freedom of the problem will be 3 into number of nodes. And that is why if you are calculating bandwidth for a 3D system, you must use 3 here. Thank you.